marine biologists in 2025 have discovered microbial communities that challenge our understanding of life in extreme environments. Recent research from Aalto University has revealed deep-sea microorganisms that produce complex sugar compounds in ways that shouldn't be possible under the crushing pressures and complete darkness of the ocean depths. These microscopic life forms have developed biochemical processes that operate efficiently in conditions that would destroy most known forms of life. The deep-sea sugar production mechanisms discovered by researchers involve bacterial communities that have evolved unique metabolic pathways. These microorganisms can synthesize complex carbohydrates without any access to sunlight, instead using chemical energy from hydrothermal vents and organic matter that drifts down from surface waters. The sugar compounds they produce are unlike anything found in surface-dwelling organisms, with molecular structures that remain stable under extreme pressure and temperature conditions. Scientists studying these deep-sea microbial communities have found that they form intricate networks that span vast areas of the ocean floor. Individual bacterial colonies communicate through chemical signals that coordinate their sugar production activities across distances of several kilometers. This coordination allows the microbial communities to respond collectively to changes in nutrient availability and environmental conditions, creating what researchers describe as a distributed biological intelligence operating in the ocean depths. The sugar compounds produced by these deep-sea microorganisms serve multiple functions that extend far beyond simple energy storage. Some of these complex carbohydrates act as antifreeze agents that prevent ice crystal formation in the organism's cellular structures. Others function as pressure-resistant structural components that help maintain cellular integrity under crushing deep-sea conditions. The most unusual sugar compounds appear to serve as communication molecules that allow different bacterial species to coordinate their activities and share resources. Australian researchers have made equally remarkable discoveries about large marine organisms adapted to extreme deep-sea conditions. Giant isopods measuring over 20 inches in length have been found living at depths where the pressure exceeds 1,000 times at its sea level. These massive crustaceans have evolved specialized physiological adaptations that allow them to survive in environments that would instantly crush most surface-dwelling creatures. The giant isopods demonstrate remarkable metabolic adaptations that allow them to survive for months without food in the nutrient-poor deep-sea environment. Their digestive systems can process almost any organic matter that reaches the ocean depths, from dead fish and marine mammals to organic debris that sinks from surface waters. When food becomes available, these creatures can consume meals equivalent to several times their body weight and then enter extended periods of dormancy that can last over a year. The pressure adaptations of giant isopods involve specialized proteins that maintain their structural integrity under extreme conditions. Their cellular membranes contain unique lipid compositions that remain flexible at crushing pressures that would solidify the membranes of surface-dwelling organisms. The isopods' nervous systems operate through modified neurotransmitter pathways that function efficiently despite the extreme pressure environment. Deep-sea exploration has revealed that these extreme environments support biodiversity levels that rival surface ecosystems. The combination of chemical energy from hydrothermal vents, organic matter from surface waters, and specialized microbial communities creates complex food webs that support hundreds of species found nowhere else on Earth. Many of these deep-sea species have evolved bioluminescent capabilities that allow them to communicate and hunt in the complete darkness of the ocean depths. The metabolic processes of deep-sea organisms operate at efficiency levels that challenge our understanding of biochemistry. Some bacterial species can extract energy from chemical compounds that are toxic to surface-dwelling organisms, converting sulfur compounds and heavy metals into usable energy sources. These extreme metabolic capabilities suggest that life can adapt to conditions far more hostile than previously thought possible. Research teams have documented deep-sea organisms that can survive temperature fluctuations from near freezing to over 400 degrees Fahrenheit near hydrothermal vents. These temperature extremes occur within distances of just a few meters, requiring organisms to possess cellular mechanisms that can rapidly adjust to dramatic environmental changes. The proteins and enzymes that enable this temperature tolerance are being studied for potential applications in industrial processes and biotechnology. The discovery of complex sugar production in deep-sea microorganisms has implications for understanding how life might exist on other planets. The ability of these organisms to synthesize complex organic compounds using only chemical energy suggests that life could potentially exist in environments previously considered uninhabitable. Astrobiologists are studying these deep-sea metabolic processes as models for how life might function on planets with no access to solar energy. The interconnected nature of deep-sea ecosystems demonstrates how life can create complex relationships even in the most extreme environments. Bacterial communities provide chemical compounds that support larger organisms, while the waste products of giant isopods and other deep-sea creatures provide nutrients that fuel microbial growth. These symbiotic relationships create self-sustaining ecosystems that can persist in isolation from surface waters for extended periods. The chemical compounds produced by deep-sea organisms are attracting attention from pharmaceutical researchers seeking new sources of bioactive molecules. Many deep-sea bacteria produce antibiotics and other compounds that show promise for treating human diseases. Unique biochemical pathways that produce molecules with properties not found in surface-dwelling species. These discoveries about life in Earth's most extreme environments reveal how much we still don't understand about the biological processes operating around us. While scientists explore the hidden capabilities of deep-sea organisms, researchers are uncovering equally surprising phenomena in the most ordinary aspects of our daily experience. Your shadow has a secret superpower. Materials science researchers in 2025 have developed breakthrough technologies that transform ordinary objects into functional devices in ways that seem almost impossible. MIT scientists have created chemical shields that can protect surfaces from virtually any type of damage or contamination. These protective coatings represent a fundamental advance in materials engineering that could revolutionize everything from medical equipment to spacecraft construction. The chemical shield technology works through engineered molecular structures that create an invisible barrier on any surface they're applied to. The coating consists of specialized polymers that form cross-linked networks at the molecular level, creating a protective layer that's only a few nanometers thick but incredibly durable. When applied to metal surfaces, the chemical shield prevents corrosion, oxidation, and chemical reactions that would normally cause deterioration over time. On glass and ceramic materials, the coating provides scratch resistance and prevents chemical etching from acids or other corrosive substances. The molecular engineering behind these chemical shields involves designing polymer chains that can adapt their structure based on the type of threat they encounter. When exposed to acidic conditions, the polymer network reconfigures itself to neutralize the acid and prevent damage to the underlying surface. Under high-temperature conditions, the same coating can dissipate heat and maintain its protective properties even when exposed to temperatures that would normally cause material failure. The adaptive nature of these coatings means they provide comprehensive protection against multiple types of damage simultaneously. Laboratory testing has demonstrated the remarkable effectiveness of these chemical shields under extreme conditions. Glass surfaces treated with a chemical shield maintain their optical clarity and structural integrity after being subjected to sandblasting that would normally cause severe damage. The coatings have proven effective against biological contamination as well, preventing bacterial growth and biofilm formation on treated surfaces. The applications for chemical shield technology extend across numerous industries where surface protection is critical. Medical device manufacturers are incorporating these coatings into surgical instruments and implantable devices to prevent bacterial infections and extend device lifespan. The aerospace industry is testing chemical shields for spacecraft components that must withstand the harsh conditions of space, including radiation exposure, extreme temperature fluctuations, and micrometeorite impacts. Automotive manufacturers are exploring applications for engine components and body panels that could significantly extend vehicle lifespans. Manufacturing processes for applying chemical shields have been developed to work with existing industrial equipment and production lines. The coating can be applied through spray application, dip coating, or vapor deposition techniques depending on the specific requirements of the application. The curing process occurs at room temperature and doesn't require specialized heating or pressure equipment, making it compatible with temperature-sensitive materials and components. Quality control systems can verify coating thickness and uniformity using standard measurement techniques. The environmental benefits of chemical shield technology are substantial because protected surfaces last significantly longer and require less frequent replacement. Buildings treated with chemical shields show dramatically reduced maintenance requirements and longer lifespans for exterior surfaces exposed to weather and pollution. Infrastructure applications include protecting bridges, pipelines, and other critical systems from corrosion and environmental damage that currently cost billions of dollars annually in repairs and replacements. Research teams have documented the long-term performance characteristics of chemical shields through accelerated aging tests that simulate decades of real-world exposure. The coatings maintain their protective properties for extended periods without degradation, even under continuous exposure to harsh conditions. Field testing on actual infrastructure projects has confirmed laboratory results, with treated surfaces showing minimal wear after years of service in challenging environments. The economic implications of widespread chemical shield adoption could be transformative for industries that currently spend enormous amounts on surface protection and maintenance. The initial cost of applying chemical shields is offset by dramatically reduced maintenance expenses and extended equipment lifespans. Manufacturing facilities that have implemented chemical shield technology report significant reductions in downtime caused by equipment corrosion and surface damage. Scientists are developing specialized versions of chemical shields for specific applications that require unique protective properties. Biomedical coatings are being engineered to promote tissue integration while preventing bacterial adhesion. Electronic device coatings provide protection against moisture and chemical contamination while maintaining electrical conductivity where needed. Food processing equipment coatings meet safety requirements while providing superior protection against cleaning chemicals and food acids. The discovery of effective chemical shield technology demonstrates how materials science continues to find solutions to problems that have challenged engineers for decades. Surface protection has been a persistent challenge across industries, with traditional approaches often providing limited effectiveness or requiring frequent reapplication. The development of adaptive molecular coatings represents a fundamental breakthrough that addresses these limitations through innovative engineering at the molecular level. Quality control and testing protocols for chemical shields have been established to ensure consistent performance across different applications and manufacturing environments. Standardized testing procedures measure coating adhesion, chemical resistance, and durability under various stress conditions. These protocols allow manufacturers to verify that chemical shields will perform as expected in their specific applications and operating environments. The success of chemical shield technology illustrates how scientific breakthroughs often emerge from fundamental research into molecular behavior and materials properties. Understanding how molecules interact at interfaces and how polymer structures can be engineered to provide specific properties has enabled the development of coatings that seemed impossible just a few years ago. This breakthrough in materials engineering represents just one example of how 2025 research is challenging fundamental assumptions about what's possible in science and technology. While